Welcome back, everyone. I hope that we're not feeling too thermoed out. I know that it's been a little bit more thermo than we usually do with the exam happening last night. So I had a chance to grade the exam submissions today. So you should be able to see your grades. I believe that I made them visible this afternoon. So the multiple choice and both long answer problems have been graded. The averages here are maybe not as high as they were in the first exam. In particular, here in question 3, there were 2 non-submissions here, so I think that brought the average down a bit. But those grades are up. I think, as I've said before, because the class size is not super large, I think if we do end up shifting grades, which does happen sometimes in thermodynamics, I will do it at the end of the class instead of in between. Also, if you look at the syllabus for this class, we also give students the option, which you don't have to exercise yourself because I'll calculate grades in different ways and give you the best option for you. But you do have the option of having the final grade count instead of one of the midterms. So if your grade on your final exam ends up being higher than your grade on one of your midterms, I'll kick out the lowest midterm grade and count your final for that percentage. Because ultimately, I'm more concerned with what you know at the end of the class than what you know either 1/3 or 2/3 of the way through the class. So have a look at those. I do try to leave comments, and particularly more comments than I think we would on a physical sheet of paper that you'd normally get, just so that you can follow along with my thought process as I'm grading. As always, if you feel like I made an error, please let me know. I am human, although, even though we're only having virtual interactions here, I can assure you that I am a human, which means that I do make mistakes sometimes. So please let me know if you feel like I've made a mistake grading your exam. So today, we're going to go through an example of Rankine reheat cycles. And now, as we move to the last third, right, the third of the class, it's going to feel a little bit like we're drinking from a fire hose, because we're going to go through, kind of in almost a rapid fire way, several different thermodynamic cycles. Now, most of those will be heat engines, but some of them will be temperature control devices like refrigerators or heat pumps. I've put all of the content online, so if you want pre-recorded lectures, if you'd like to do that either to review what we're doing here in class, or if you'd like to get ahead of the class, you're certainly welcome to watch these lectures. So if you click, I think week to week I have all the videos, but if you want the starter sheets that we're going to use to do these problems, then you can click on this tab under content called Scherzer's Pre-Recorded Lectures and Starter Sheets. And then for each lecture, I have a link to the YouTube video of the pre-recorded version of this lecture. Plus, I have a link to a PDF of the starter sheet. So in this particular class, if you click on that, you'll get the sheet that shows you what problem we'll be working on today. So you're always welcome to sort of hit those up in real time, or to download them before the class, or after the class too, if you want to review how we're doing these. So those are there for your reference. Normally in class we would pass these things out, but virtually we're sort of stuck downloading them like this. So just a reminder, and it doesn't always feel like this the day after an exam, but I want you all to remember that thermo is awesome, right? So this is a class where we're really trying to understand how the universe works, right? It's about these energy transactions that are happening all around us, and really how, as engineers, we can try to bend the universe to our will by understanding how energy moves from one place to another. And as engineers, again, we're trying to creatively control how these interaction happens to try to, develop some kind of a social good. So we've been talking about these heat engines, where the heat engines are turning heat in, right? So often we're generating heat either by burning something like coal, or in a Rankine cycle also producing heat through a nuclear reaction, and we're turning that into net power. Now, for Rankine cycles, we're typically putting that power out on the grid. So this particular equation for thermal efficiency will always be true for heat engines, right? But if we want to look at specifically ideal heat engines, or what's the highest efficiency we can get, because we all know, hopefully by now, that the highest efficiency we can get is not 100%. So we're limited because of the second law and the irreversibilities that always happen, right? So for a heat engine, we know that Kelvin and Planck told us that heat engines get hot, so they need some place to reject heat. They need some heat sink, which means we can't turn all the input heat into work. So the Carnot efficiency gives us some idea of the maximum efficiency that we could get, theoretically. And even that we can't actually get, but we can kind of asymptotically approach that performance that's given by the Carnot equation. We talked about the importance of Rankine cycles here in the United States, and although the amount of power that we generate using coal power plants and nuclear power plants is falling as we sort of increase dependence on natural gas power plants and kind of slowly increase renewable power generation as well, it's still an important way that we generate energy. So again, according to this government website, so in 2019, Rankine cycles through coal and nuclear power plants generated about 45% of the energy that we use on the grid here in the United States. Now, we did a Rankine cycle in example previously, this 4-component Rankine cycle, and we found that the thermal efficiency here was 28.4%, right? And then so I made the argument over the last couple classes that we can increase that efficiency. And we can't get to 100%, but we should be able to get closer to the Carnot efficiency, which I believe in that case was somewhere in the mid-50s. And there's benefit to doing that, and there's financial benefit to doing that, and there's environmental benefit to doing that. And I think as engineers, it's important that we're concerned with both of those two aspects of practical problems. We talked about how one of the ways that we can improve thermal efficiency is by sort of developing our own skills, kind of becoming master builders, right? So if we think about this 4-point Rankine cycle, or this 4-component Rankine cycle as kind of the base model, right? So if we can do the 4-part Rankine cycle, you know, that's an important thing because it lets us understand the principles that are involved with making this type of heat engine. But one of the ways that we can improve the efficiency of this kind of Rankine cycle is by increasing the complexity. So if we go from making these sort of less complicated Rankine cycles to something that's more extravagant or more complicated, the benefit of that is that we can improve our thermal efficiency. Last class, we talked about one of the ways that we can do this by adding a second turbine. So here, instead of just having one turbine, we split the power generation between 2 turbines. So we have a high pressure turbine where the fluid's coming in right out of the boiler or the steam generator. So this is high temperature, high pressure steam. We run that through the turbine. And if this was kind of a normal 4-component cycle, then we would run it through the whole turbine, right? But about halfway through or some part through, we're losing pressure, but the enthalpy is dropping too. So the benefit of splitting the turbines like this is that after we go through the high pressure turbine, then we can heat that fluid back up. So we can put more enthalpy into the steam. And by doing that, it means that we can get more work out of this low pressure part of our power generation process, right? So this low pressure turbine. And we kind of already have this steam generator here. So we're putting more heat into the system because we have to kind of reboil or reheat this steam. But it's less energy than it takes to get from a liquid at high pressure, right? Because here we're probably going to be either some high quality mixture or maybe even still superheated vapor. So we're putting enthalpy in here, but it's at a lower cost in terms of heat rate than heating it up right from a liquid. So this is called a reheat cycle because we reheat the working fluid, right? And it's kind of odd, right? And maybe it's a bit embarrassing when I say this, but for me, when I'm doing the analysis of this particular type of cycle, if there's a process that I forget, it's not the turbines, because I can see here, it's a whole different component. I usually remember that I'm adding a second turbine here, but sometimes when I'm calculating the heat in, I forget that there's this second heat addition process. So the total heat in is going to be the heat as we move from state 6 to state 1, plus the heat that we add as we move from state 2 to state 3. So it's not just a heat cycle, it's a reheat cycle. You have two processes where we're adding heat. It's important to be able to draw the TS diagrams, and this is a TS diagram for a cycle like this from the textbook, showing isentropic turbines and pumps, because these are vertical lines as I move from 1 to 2 and 3 to 4, and also isentropic pumps from 5 to 6, right? But what happens here is after we go through the first turbine, right, this is vertically down, but we stop at some intermediate pressure, right? We have some low pressure down here, some high pressure up here, and some intermediate pressure that's the exit of the high pressure turbine, but also the inlet to the low pressure turbine. But in between the outlet of the first turbine and the inlet of the second turbine, we heat this fluid back up. We add more enthalpy by increasing the temperature. Just like in the boiler or the steam generator, we're going to assume that that happens at constant pressure, right? Or at least that's kind of how it's drawn in this particular case. Now, when we're talking about our thermal efficiency, it's still going to be the energy benefit divided by the energy cost. And this is a heat engine, so the energy benefit is still net power, and the energy cost is still heat in. But in this case, we have three components that have to do with power. So we have two turbines that are producing power and one pump that's consuming power. So I add up all three of those terms. Now, I think we mostly avoided making this mistake on the exam, but we got to be careful of the signs. So my advice, because I think it's less confusing, is to use expressions for W dot like you would derive them from the first law. So that W dot is always going to be M dot times H in minus H out. And I say always, but it's really provided that we can make all those assumptions we're used to making for turbines. Now, if we can do that, then we add them all up and we don't subtract the pump power, because the pump power is going to be negative. So if we subtracted the pump power and we let hip to win figure out what this sign should be, and we get this from the first law, then we'd be subtracting a negative, and it would look like we're adding power by putting the pump in when really we're subtracting from the net power. In the denominator, again, this is usually the part that if I'm going to mess up, the part that I'll forget is I remember that we have to heat the first time, but I forget that this is a reheat cycle, which means that I have to heat the second time as well. So the heat in is now not just this process from 6 to 1, but also this process from 2 to 3. So the process is generally the same as a 4-component Rankine cycle. So even though we're increasing the complexity here, the process is going to be the same. It's just we have more components, right? But if we know how to go through and systematically do a 4-component cycle, doing this reheat cycle hopefully doesn't seem all that much more confusing, except that our thermal efficiency equation is different. The first law for turbines, pumps, and boilers, right? So we would say that we have all of these processes at steady state in this class. Typically, these processes will have one inlet and one outlet. We typically neglect kinetic and potential energy. For these components, if I'm talking about turbines and pumps, I'll usually say that they have no heat loss. Although if I was given a heat loss, I'd have to be able to deal with that. But then I'd also say that the boiler and the reheat process are passive, or that they have no power. If that's the case, then I'll get these expressions, which hopefully are starting to feel pretty familiar. So my turbine power is going to be M dot times H in minus H out. My pump power is going to be M dot times H in minus H out. And if I'm trying to find a heat rate, whether it's from the boiler or from the hot side of the condenser, it's going to be M dot times H out minus H in. Here, I also know something about the signs just from my intuition, because the turbine is producing power, or in this case, both turbines are producing power, they should have positive powers. The pump is consuming power, so it should have a negative power. That's why I need to add them together if I'm doing if I'm trusting the first law. If I'm not, what I would try to encourage you to do is put absolute value signs in front of these things when you're writing out the net power, because that will remind you to do this part correctly. Because here in the pump, H out is bigger than H in. So the textbook will tell you that pump power is m dot times H out minus H in, but you can't get that from the first law. So I don't particularly like that formulation. We know that when we're adding heat in the boiler or in the reheat cycle or in the reheat phase, then it's going to be a positive number. And the heat that we're rejecting in the condenser from the hot side is going to be negative. So all of this so far looks pretty much the same, right? Pretty much the same as a 4-component Rankine cycle. This, I think, was borne out to be true on the exam. The hardest one, I think, to calculate here, right? Because we got to ask what's the fluid to find these delta H's. Delta H across an isentropic pump, right, or an ideal pump, is going to be the specific volume. Usually one of the cases will be saturated liquid, so we'll use the specific volume of the saturated liquid. If it's water, that's usually about 1 divided by 1,000. So it'll be that specific volume times the change in pressure, right? So if we're talking about a Rankine cycle or a Rankine cycle with reheat, the working fluid is going to be water, or at least something like it that's bouncing back and forth across the vapor dome. So hopefully this part is making sense, right? So what we're going to do today is we're going to go through an example of one of these reheat problems, just so you can see how we would go about solving it. So on that handout, it gives us this state table. So this state table has only the states inside sort of the Rankine cycle part. So on the exam and in a previous example we also talked about the cooling water, but that's not here. So we have the inlet to the high pressure turbine at state 1. We have an ideal and a real outlet from that turbine. Then the inlet to the second turbine, an ideal and real outlet. Then we go through the condenser, right? And then we, as we move through the pump between state 5 and 6, we have an ideal outlet from the pump and a real outlet from the pump. We're also told that the isentropic efficiencies of the turbines, and I think the pump in this problem, are 85%. We're asked to find the thermal efficiency of this particular cycle, because I've been making the argument that doing this reheat improves efficiency. So, we'd like to be able to test if that's true. Now, the thing about science is we can never prove something is true, right? We have a hypothesis and we test the hypothesis. And if we support the hypothesis, we don't say that thing is true. We just say that we supported the hypothesis. But if that thing is false, if we find here that thermal efficiency decreases, then we know the hypothesis isn't any good, right? So let's do the example, right? Now this is in the textbook, so I mean maybe we have some idea how it's going to turn out, right? So I don't want to spoil the surprise here, but thermal efficiency will increase, right? So we know that the thermal efficiency for these heat engines is going to be net power divided by heat in. And in this case, the net power, because we have 2 turbines and a pump, the net power is the sum of the 2 turbines plus the pump power, which I know is negative. And then we're going to divide by the 2 places where we're adding heat. At this point, I don't know the power from the first turbine. I don't know the power from the second turbine. I don't know the power from the pump. I don't know the power from the first heat addition process or the second heat addition process. So it's great that I have this equation. It's less great because I got one equation with 6 unknowns, because I also don't know the thermal efficiency. So I'd like to get to the point where I have one equation here and the only unknown that I have is the thermal efficiency. So as we said, what we can do here is we can look at each individual component, right? So we can always do this in one of these cycles. If we were talking about an ideal cycle, then we can look at the temperatures of the hot reservoir and the cold reservoir. But for real cycles and for ideal cycles, we can always go component by component. So that's what we'll do. We know that all of these different components we'll say are at steady state. There's always going to be one inlet and one outlet in this particular cycle. We're going to neglect kinetic energy changes in all processes and potential energy changes in all processes. We're going to go through each process. We'll say that turbines and pumps are adiabatic, and we'll say that heat addition or rejection is going to be passive. So we'll selectively get rid of either Q dot or W dot, depending on what the process is asking us to do. We're also going to say that in between the different processes, there are no friction or heat losses. We do this because we want to fix fewer states. So we don't want the exit of the first turbine to be a different state than the inlet to the reheat cycle or the reheat process. I think there's one homework problem we'll see where they don't neglect these things. They take into account these things, and it means you have to fix a lot more states, right? So, and I think ultimately the benefit you get from it, you will get more accurate, but this is always the job of the engineer. Part of the reason that you can justify your first world salaries is that you'll have to make assumptions that make sense, right? You'll have to take real problems and turn them into problems that look like textbook problems, right? So you want to get a reasonable answer for whatever your application is, right? So only you, or at least people you're working with on the problem, will make some judgment about what kind of level of accuracy is acceptable. And then you'll have to see if the assumptions that you're making land you in that area of acceptable accuracy. So if we do this, then for the high pressure and low pressure turbines, we're going to get m dot times h in minus h out. Those will be positive power terms. The pump will also be w dot is equal to m dot times h in minus h out, but that term will be negative. Both places where we're adding heat are m dot times h out minus h in, and we expect both of those terms to be positive. Now, if the problem asked me, I could also find how much heat was rejected, right? Or as we saw on the exam problem, it said kind of like, how do I figure out what the mass flow rate I need of this cooling water, right? So if I was pulling cold water out of sort of, towards the bottom of Lake Ontario where the water is stratified and cold, then I might want to know how much water do I have to pump, right? So it's an important problem to say how much of that cooling water do we need, but it's not a problem that's asked in this particular question. So we're not going to talk about the condenser heat, but if it was here, it would also be m dot times h out minus h in, and we would expect that to be negative. So on all these components, right, because if you look over here, I have different m dot terms for each component, the two turbines, the pump, and the two heat addition processes. So I need to see, is that a reasonable thing, or can I sort of consolidate the problem so there's only one mass flow rate? So in this case, all of my components are at steady state, and all of my components have one inlet and one outlet. This is kind of a happy situation because this means if I look at every single one of these components, they're all going to be m dot in is equal to m dot out. And since the outlet of every component is the inlet of the next component, there's only one mass flow rate in this problem. So I'm going to get rid of all these subscripts and only call m dot, right? So there's only one m dot in the problem. So this is nice because when I look at my thermal efficiency, I'm going to put in all the equations that I have, right? So this is the first turbine power, the second turbine power, the pump power, and the heat addition terms. All of these terms are m dot times something. And I think this problem didn't tell me what m dot is, but it turns out that doesn't matter, right? Obviously, it matters for what the net power is, but in terms of the thermal efficiency, it doesn't matter because m dot is a factor in all the terms in the numerator and all the terms in the denominator. So we can cross all of these m dots out, and I'm left with a function that tells me the thermal efficiency as a function of all the enthalpies, H1, H2, H3, H4, H5, and H6. Notice that there's no H2S, H4S, or H6S here, right? So in my thermal efficiency equation, I never talk about the ideal outlets of these different components because those things aren't real. They don't exist. But finding them will help me to find the real outlets, and it's the real outlet enthalpies that I need in my thermal efficiency equation. So now in some ways it feels worse because, I added more terms, and a lot of these terms I don't know. But this is kind of always the state we want to get to in thermodynamics, because if I can fix all of the states in my problem, then I'm going to have one equation, and the only unknown will be the thermal efficiency. So let's work through this and see if we can get this, right? So at this point, we know H1, we don't know H2, we know H3, we don't know H4. Excuse me while I close this. We know H5, we don't know H6, right? So this is true in the numerator and the denominator, even though this says we do know H6. So this one should be an X here too, because we don't know H6 in the numerator or the denominator. So what do we do, right? I'm staring at this state table, right? And, when you get a state table on an exam, sometimes there's this feeling that you have to fill the whole thing out. And that can be true. That could just be a problem, right? Part B or something on the test could say, fill in everything on the state table. But I always like to do the symbolic equation first, because then I know what are the things that I actually need to fix. So I'm not wasting my time, in this case, solving all the specific enthalpies if I don't need them in the equation that I'm using to get my final answer. So, isentropic efficiencies. So here, right, so I know something about the inlet to the first turbine, right? Now, maybe I can use the isentropic efficiency of this turbine to find the real outlet, right? And if that's true, I know that the power developed by the real turbine is going to be less than the power developed by the ideal turbine. So this is W dot real over W dot ideal. So for each of these turbines, it's going to be H in minus H out divided by H in minus the isentropic outlet of the component, right? So this is true for the first turbine, and it's true for the second turbine. So here, what I would actually like to do for both of these cases is find the real outlet. So I can take this equation up here and manipulate it so I isolate H out. If I do that, I get that this is going to be H in minus the isentropic efficiency of the turbine times H in minus the isentropic outlet. So unfortunately, right, so I don't know the real outlets and I don't know the isentropic outlets. So for both turbines, I'm going to have to figure out how I can find the isentropic outlets of these turbines. So what do I know about the word isentropic? Isentropic, it's kind of secret code for ideal, but it's only ideal if a process is steady state, adiabatic, and there's no entropy generation. And if that's the case, then from the second law, I can see that across, a process like the turbine or the pump, I'm not going to get any change in the specific entropy. So if I'm trying to find state 2s, it looks like I only know one independent, well, I guess it's always independent if I only know one piece of information, right? But I only have one intensive property here. But I know, because 2s means the isentropic outlet, that I also have the same entropy, the same specific entropy at the outlet of the ideal turbine as I did at the inlet of the ideal turbine. So now I know the pressure and I know the specific entropy. So at this point, what I'd have to do is look on a table, figure out that if the pressure is 10 bar, what's SF and SG? So if this is in between SF and SG, that would mean I'd have to find quality because I'd have a two-phase mixture. But if it's greater than SG, then I know that I'll have to find some kind of interpolation in the superheated vapor region. So in this case, we can find our S2S is 6.8778 kilojoules per kilogram. That was the same as at the inlet. I look for my table. So in this case, I looked at the superheated vapor tables. I see that at 10 bar, the saturation temperature is 180. So if I knew the temperature and if I knew that I was above this, then I'd know that I was superheated vapor. But that's not what I have. Instead, I look at this is the specific entropy of the saturated case. That's when the temperature is 179.9991, sorry. So this is 6.58, and you see how it goes up with temperature? And this is bigger than 6.58. So that must mean that I'm superheated vapor. So now I see that my value for the isentropic outlet is between 200 and 240 degrees because we're between this 6.7 and 6.88, right? We're pretty close to 6.88. So if this was a test and I was running out of time, I'd say, well, Dr. Schertzer, we're pretty close to 240 degrees here, so I'm just going to take that number. But in this case, I'll find my coefficient here for the interpolation, and I find that this is just about 1, which I can see here because, you know, I'm at 6.878, right, instead of 6.882-ish, right? So we're just about equal to that, and I find that H2S is just under this 2920, right? So it's 2,919.7 kilojoules per kilogram. So this is good. I can put this in my state table, and now I know the isentropic outlet for the specific enthalpy of the first turbine. Since I've already done this, I'm kind of already in this kind of mode, so I'm going to jump down and do the same thing for the isentropic outlet of the second turbine. Right, so here again, my isentropic, because this is an isentropic process, S of 4S is the same as S3. Right, so again, now I have this specific entropy. I know the temperature is 95 degrees, so that's this line. I've kind of jumped on top of this line a little bit. But here I see that my 7.3 is between SF, which is 1.25, and SG, which is 7.41-ish, right? So here I'm in between these two values. So now when I'm interpolating, what I need to find is the quality. The quality, this is going to work just like my interpolation factor, right? So my quality equation is going to tell me, again, that I'm pretty close to this saturated vapor here, right? So I have a pretty high quality. It's mostly saturated vapor, but there's a little bit of saturated liquid in there. But once I find X of 4S, right? Because here I had this quality equation and I knew all these S's, right? That helped me to find X. But now when I have all these H's, I only know HF, HG, and HF. But now I know X4S. So the only thing I don't know here is H4S, or the specific entropy of the isentropic outlet of the low pressure turbine, right? Which is a bit of a mouthful. But the math here is hopefully not too bad. And I see that H4S is very close to HG because my quality is pretty high, right? So here I'm feeling pretty good. I have the isentropic outlets of both turbines. So now what do I want to do? Because I want to get the real outlet of both turbines. So I'm going to do this in parallel as well. So it's going to be the same equation, right? So we know already, we derived the equation already from the definition of isentropic efficiency for turbines, that H of the real outlet is going to be H in minus the turbine efficiency times H in minus H out of the isentropic turbine. Now I know everything here except H out. So I can put some stuff into my calculator and I see that H2 is going to be just under 3,010 kilojoules per kilogram. And H4 is going to be 2,705.7 kilojoules per kilogram. So now I filled in these particular pieces of information and I'm feeling pretty good, right? Because when I was looking at my isentropic efficiency equation, the things that I didn't know were H2, H4, and H6. And now I already found H2 and I already found H4, right? Now, oftentimes, if, so on a test, you wouldn't necessarily, and I think on the test last night, we didn't get the isentropic outlet of the ideal turbine or the ideal pump. So we had to calculate this using V times delta P, right? But here in this problem, they're nice to us. They give us H of 6S. So now as I go to state 6, I say, okay, how do I get the specific enthalpy of the real outlet of the pump? And the answer is, again, here I know the isentropic efficiency of the pump, same as the isentropic efficiency of the turbines in this problem. But now it's switched over, right? Because the pump power here is an energy cost. right? And the irreversibilities are always kind of working against us. So for turbines, the power was a benefit. So it reduced our benefit. For the pumps, the power is a cost, so it increases our cost, right? So in this case, the ideal pump consumes less power than the real pump. So here I put the delta H for the ideal pump, right? H in minus the isentropic outlet over the real pump power, at least the specific power here, because the m dots across the real and the ideal pumps are the same, because otherwise it wouldn't really make sense to compare an ideal turbine to a real turbine or an ideal pump to a real pump unless their mass flow rates were the same, right? So it's like everything else is the same except it's got this isentropic outlet, right? So the m dots drop out. On the bottom, I have H in minus the real outlet. So in this case, I know the isentropic efficiency of the pump. I know H in, it's given to me. I know the isentropic outlet enthalpy, but what I want is the specific enthalpy of the real pump, right? So this is the thing that I don't know here. So I have one equation and one unknown. I have to do a little bit of manipulation here. And you see that this equation ends up looking kind of similar, but kind of different to what we saw with the turbine, right? Because this, this power relationship is inverted here. So now we're going to get H in minus H out of the isentropic pump divided by now the turbine efficiency. Because here, this should say pump efficiency down here. Sorry about that. So what this happens here is because we're dividing by the turbine efficiency, that's going to make this change bigger because we have a bigger change in H across our real turbine. Sorry, our real pump. Right? So when I put this in, my H6 becomes 407.3 kilojoules per kilogram. So now I can put this into my state table along with, I have H2, I have H4, and now I have H6, right? And that's good because now I look back, right? If I was doing this all on one piece of paper, I would look at my isentropic efficiency, my symbolic solution that I found, and see that it's a function of all the enthalpies, 1 through 6. And now I know all those enthalpies. And that means I'm almost done the problem. I just got to not put the numbers wrong in my calculator, which for me is always challenging because I'm really good at putting the numbers wrong into my calculator, right? So here, it's worth double checking, right? But here, right? So I have these turbine powers. I add those to the pump power, but the pump power is negative, right? So here, right, we're going to get these turbine powers are going to be positive, but the net power is going to come down a little bit because I have this pump, right? So you can always kind of think about this while you're doing the math. And again, maybe it's because my calculator is maybe not as fancy as your calculator, or maybe it's because I'm, I got this drilled into me when I was an undergraduate, but it's good to slow down. It's good not to do 3 steps in one line, right? Because if I do this, if I had this as a negative and this as a negative, and I wrote this all out in a line, I'd have that opportunity to say, oh, it doesn't really make sense that pump power is increasing my net power, right? So here I got a chance to look at this, right? I put some numbers in. I see that the numerator is smaller than the denominator, which I'm expecting because I know that this efficiency has to be below 100% for sure. And I think that if we were still treating this the same as the last problem we did, then I think that the thermal efficiency maximum was something like 55%. So here we get that our efficiency went up to 29.2%, right? So this is bigger than 28.4%. And you might be thinking, like, well, who cares? It went up by 0.8%, not even a whole percentage point, right? But if we think about this, right, for all the coal that we shovel in to some kind of burner, right, so that we can boil water, this means we reduce that by 1%, right? And that's a big savings in emissions considering that, we're generating power all the time, right? And if this was a nuclear reaction and the nuclear reaction was putting out a certain amount of heat, improving this efficiency means that we're getting more work out for the same amount of heat. And it's a big deal, right? So even though the number seems small, um, because we're running these things constantly and we're producing and consuming so much power, even small changes in efficiency like this, or changes in efficiency that look small, have really big financial and environmental impacts, right? So this might look like a small thing, and in a real, Rankine cycle, like if you go to a nuclear power plant, they're doing lots of things, right? So they're going to be running multiple reheats. They're going to do regeneration, which we're going to learn about next, and all of these things work to improve efficiency. And if you could go into a power plant and improve the efficiency by 1%, you would certainly be earning your first world salary if you did that. Okay? So that is all that I have for you today. I'm happy to stick around and entertain any questions that you might have. Thank you. All right. Have a great week.